All right, so today we're going to be doing our exam one review, about things like trees, balance trees, and heaps, so everything we've discussed so far this semester. So hopefully, yeah, nothing new, just kind of a review. But hopefully if you missed anything this semester so far, this will be a good refresher. Okay. So our objectives are to go over trees and traversals, and then balance trees, and then finally keep some priority queues. These are the kind of things you'll have to know for the exam. For trees and traversals, terminology, types of trees, traversals, and so on. Yeah, just things like that. For balance trees, you don't need to know pseudocode for this. For balance trees, you're gonna have to know like different types of balance trees, so like splay trees, BMB plus trees, red-black trees, ABL trees. You don't have to know pseudocode for any of them, because that would take too long on an exam. You also know pseudocode in general, it's not for balance trees. And then for heaps of priority queues, you'll have to know properties, pseudocode, and representing heaps, and insertion, deletion, and heaps. And pseudocode there because it's a little bit simpler than like balance trees, hopefully, and less expensive. But okay, let's dive in. So for trees and traversals, that's the first thing. So for trees, trees are a data structure, in which each node has a value and a list of references to other nodes or its children. So this can be like having a left and right child, like we see here with this node here. That's, for example, a type of tree structure, right? That's an example of a node. You might also have like a list, like a vector of nodes, node children, and that's also fine, right? That's also a valid tree structure. Different kinds of trees which discussed in this course so far are like general trees, and then binary trees, which are trees in which have 2 or fewer children for every node. Binary search trees, which are just binary trees with the property that everything to the left is smaller and everything to the right is larger in every subtree of the root of that subtree. AVL trees, which are balanced binary search trees, and red-black trees, which are also balanced binary search trees, although they're balanced differently, right? They're balanced based on the color. For red-black trees, we'll get to what you need to know for those, but it's really just the 4 properties of red-black trees. Splay trees also, there's only like 1 property you have to know. And then n-ary trees. So n-ary trees are just like trees that may have up to n children per node, or like each root of every subtree has at most n children. So a binary tree is just like a 2-ary tree, right? Okay, so that's trees. We only need to know tree traversals. So tree traversals, things like pre-order, in-order, and post-order. And so if you remember, like pre-order is like node left, right? In-order is left node, right? And post-order is left, right node. And so this is really just what we talked about when we went over tree traversals in the past, where like when we went about this, if you want to do a tree traversal, let's say on this one, if you want to do a pre-order, then you go like node left, right. And when you see n, you cross it out and like write an a here, right? Because you visit it. N just means you visit, and then the next one you know is left, right, and then you have node left, right here. And the first thing is you get node, so you get b, and so on. And so whenever you see node, right, you cross it out, you visit it, left, you go to the left subtree, and right, you go to the right subtree. And so that's tree traversals. In order and post order, similar, just different order, right? Pre, node comes first, in order, node is in the middle, and post order, node goes to the end. But left is always before right for these traversals. These are examples of depth first searches, right? In a tree. Okay. So question for you guys. So what is the third node to be printed out in a post-order traversal of this tree?
Four.
Okay, let's see.
Wait, hold on.
Oh yeah, sorry, I'm not
Okay.
sure. I haven't gone through it yet.
Oh, okay. Then just go through it.
Okay, yeah. We can go through it. And yeah, it might be 4, is what I'm saying. I don't know yet.
Okay.
So, oh, sorry, it's post order, not pre-order, so it's left, right node. So, okay, so go left first.
Oh, I did not do post order. Hold on, let me do it again.
Okay, yeah, sure, go for it.
Okay, I think 7.
Okay. I think it is 7. Yeah. But yeah, that's always tricky. You always have to make sure you're doing the right one. Sort of, you know, so yeah, left, right node. So we go to the left subtree. So left, right node. Go to the left subtree. And here the first one we're going to visit is 1. Try left, right, try right, and try node. We go up to the 3, try the right subtree. Here we go left, right node. Let's try the left one. Here we also do left, right node. Can't go left, can't go right, so we get the node 4. We go back up to 6 to try the right subtree. Left, right node, can't go left, can't go right. But we can grab the node, we can visit it. So 7 is the third one. So yep, right, 7. So for post order, 7. And if you wanted to just do this as an exercise, you can go through the other ones as well. Okay. So now we're going to talk about binary search tree operations. So binary search tree operations, there are 3, right? There's search, there's insert, and there's remove. And the time complexity of all of them is the same. They're all log n, right? And yeah, and we'll look at search first because really search is kind of the dominating time complexity of the 3 of them. Like in all 3, in order to insert, you have to find where you want to put the node. For delete, you have to find the node first, and for search, you have to find the node. So in all 3, like the thing that takes the most time is search, and search is log n. So all of them are log n because the thing that takes the most time takes log n time. The reason why it's log n is because the height of the tree is log n, right? Because there's a balance, or sorry, for a balanced binary search tree. That's why it's the average case. It's because in average, we're saying it's somewhat balanced. In general, that may not be the case, right? So in the worst case, I'm not sure what's on here, but in the worst case, search for a binary search tree at O(n) time, because in the worst case, like you could have something that's completely like right skewed, for example, where it's just like basically a linked list. So it can look something like this. Might still be a valid binary search tree, but notice it's not balanced at all. So the height of it is O(n). So if the height of it is O(n), then search takes O(n) time. But on average, like if it's balanced, then we're expecting it to see log n. But yeah, if it's not balanced, like if it's just a general binary search tree, then the search could take up to O(n) time. And it's O(n) time because you have to go through every node. You have to go through every node, and you have to go through the height of the tree, basically. You have to go through the number of nodes equal to the height of the tree. So if the height of the tree is log n, it's balanced, then search takes a log n time. But if the height of the tree is O(n), it takes O(n) time. So it really depends on the height of the tree, so whether it's balanced or not. Yep, and that's how you decide. Then, and this is what the code would look like, right? Notice how in this code, we have our base case, the root is null, or we already found the key, you just return it, right? Null, you didn't find it, root equals key, or the key, root's key is equal to the key, you did find it, so return it. If it's less, you go into the left subtree, and if it's greater than, you go into the right subtree. Insert is similar, except notice that for insert, rather than, and the time complexity of insert is exactly the same as it was with search. In the worst case, it's O(n). In the average case, it's log n. And just as before, if it's less than, then we're going to insert into the left subtree. So it's going to look like this. If our key is less than the node's key, you insert on the left. And if it's greater than, you insert on the right. But if node is null, so the tree is empty, you return a new node. That's it. But otherwise, you're going to return node. And you're going to return node because you're trying to, you're trying to insert. Yeah, so this is, if here, in this case, like if you already found it, or like if you already found it, so either you've already inserted it, or you either already inserted it or it already exists in the tree before you even tried, then you're just going to be returning the node. And so this allows the recursive calls to like go back up properly because you're inserting on the left and on the right here. But if you have some subtree in which you haven't already put it in, then you're returning this new node key. So like it might look something like this, where you found where you're trying to put it. You're trying to put it off to the right here of this node as an example, right? If you're trying to put it off to the right, then you return new node key. So that creates a new node. And if on the last recursive call, you had done something like this, node right equals insert this, then this insert, this thing is going to return this new node. And when it returns the new node, like creates a new node. And then because the previous call had said that's the previous guy's right child, then it's going to be the right child. So that's why this recursive call works. That's kind of how this code works, is that, yeah, if you have a subtree which is empty, then that's where the node goes. If you already found the node, then you can just return. You don't need to change anything. But if it's left, you insert on the left, and if it's on the right, you insert on the right. Remove is similar also, but it's just a bit longer. So delete. Delete an element by using comparisons to determine whether to go left or right. If the root is null, you return your root, right? Because that's just your base case. Like you don't return anything if there's nothing there. Otherwise, you have to keep going to the left or to the right until you find where you need to go. So if it's left, then you delete node on the left. So this is just like with insert. And if it's greater, then you go to the right. But once you have found the node you want to delete, then you go into this else block. And in this else block, if the left is null, then you have to take the one on the right. And then, yeah, you delete your node, or you delete your root, which is your current node, and return your temp, because temp is equal to the roots, right? So basically, you're just like deleting this one and making you're basically just like, if there's nothing on the left, then you can just take the right child. And like, if the tree looks like this, what I'm trying to say, and you want to, there's no left child here, right? And the node we want to delete, let's say, is this node. Then essentially what this code does for this if statement is it just takes this and makes this the child and deletes this node. And the reason why this works is the same reason why we had the insert work, is because of this line here, right? It's like root left, or in this case, be root right. Root right equals node. So because we're returning this node here, and previously we wanted this guy's right child, this guy's right child is this one. And yeah, because we delete this one, it works fine. We don't have any memory problems. And the same thing is true on the left side, right? If the root's right is null, so if the right side is null, then we just do the same thing but for the left. So it's just the opposite side, but it's the same idea. However, that covers the one child case. If there are two children, then you find the in-order successor, right? So you find the smallest value in the right subtree. And then just like swap the values of that in-order successor with your current node. And the in-order successor is going to be a leaf. So then you just delete the leaf. Like you swap the values over and then delete that one, because that one, its values are now somewhere else. Right? You don't need it twice in the tree. So you just delete it. So then you delete the in-order successor after making this node have the contents that the in-order successor had before. Then you return your root. That's how to delete it. That covers this code. And the average time length, as mentioned, this is also log n because you have to go through the height of the tree. So the average height is log n, but the height could also be on. So in the worst case binary search tree, delete is on. But for a balanced binary search tree, then it's log n. So we'll talk about balanced trees. So AVL trees are a self-balancing binary search tree in which the balance factors for all nodes have a magnitude less than 2. So the balance factor can be -1, 0, or 1, but that's it. Since it stays balanced, insertion, deletion, searching are log n because the height of the tree is log n. And that's because it's balanced. So yeah, and you check balance factors after every insertion and deletion, and then it'll rebalance with rotations. For your project, I believe you didn't have to worry about it for deletions, right? You only have to worry about it for insertions, which is fine. But in general, for AVL trees, deletions, you may have to also, for general AVL trees, you do have to rebalance with deletions. Obviously, we're not going to ask you to like write code for that, but just knowing that's the case, that balance factors have to be checked and rotations have to be done after every insertion and deletion. Okay. And remember the different types of imbalances. You have left imbalance, you do a right rotation. And for right imbalance, you do a left rotation. For left-right imbalance, you do a left-right rotation, which is a left rotation on the middle node, followed by a right rotation about the root of the subtree. And then right-left imbalance, you do a right-left rotation. So right rotation around the middle node, followed by a left rotation about the root. So for this one, after you insert 5, what's the root going to be? So it's a good question, I guess, for you guys to try and think about. So we can go over this problem. For this one, let's insert the 5. Notice it's a binary signature, so we can insert it. We insert 5, and notice the 5 is less than 10. So we insert it to the left of 10. And it's less than 6, we insert it to the left of 6, but it's larger than 4, so insert it to the right of 4. So this is what the tree is going to look like before we do any sort of rotation. We have to check now. Is there an imbalance? And there is, right? And we can check the balance factor. So 5 has a balance factor of 0, 4 has a balance factor of left minus right, -1. 8 has a balance factor of 0. 6 has a balance factor of the height of the left is 2 and the height of the right is 0, so we have 1. 14 has a balance factor of 0. But notice the 10's balance factor here is actually 2, because the height of the left is 1, 2, 3, and the height of the right is only 1. So 10's balance factor is 2. So this is unbalanced after we insert 5. So now we have to do a rotation. What kind of rotation? Well, we have to figure out where the imbalance comes from on the 10. Well, the imbalance comes from the left child's and the left child's left child, because the imbalance is on the path. Like if we trace the path from where the imbalance is down to what causes the imbalance, right? We notice that it's from the left child and the left child, left child. Left child's left child. Yeah, so a lot of left child. But anyway, yeah, that's what we find, and we find it right here. So this kind of imbalance is going to be a left imbalance, right? So left imbalance, I don't know, I can't really spell. But anyway, it's a left imbalance, right? So we need to do or left imbalance rather. So we need to do a right rotation about 10. And so when we do the right rotation, what that means, we're doing like this. So let's see an animation of it on the next slide. So first we have the balance factors. Insert 5 like normal, 10 becomes unbalanced. Well, okay, these are poll questions, but I guess we kind of went over the answer, but let's see. So we do the right rotation, and this is what we get. The 6 moves up, but if we just did the rotation, it would look kind of weird, because if we just did that, right, like you can't just like pick up the 6 and have it, the other ones kind of drop into place, because then 6 would have 3 children, which is impossible. So what we can do is notice 10 will no longer have a left child, because 10 becomes the child of 6. But 8 is on the right of 6, but on the left of 10. So 8 is greater than 6, but less than 10. So we can make this right subtree of 6 the left subtree of the root from before, if that makes sense. And so now 6 will become the root. And then we'll have 10 as the right child and 8 as the right left grandchild of the root. And that's it. And that's how we get this. So we do a left. We have a left imbalance, we do a right rotation. Okay. So that made sense. And the root is 6. Now I'll talk about red-black trees. So red-black trees are an alternative to red-black trees. Yeah, thanks. Okay, so yeah, red black trees are an alternative to the yellow trees. They are the basis for the C++ map class. So for ordered maps, that's what they're implemented with is red black trees. It also uses scheduling algorithms. But again, the main thing you need to know about red black trees for the exam is just these things here, these 4 things. A node is red or black. The root is always black. A red node always has black children. So you can't have a red node followed by a red node. Black nodes can have black or red children, right? Because of course they can, right? There's no problem with that necessarily. And then null references are considered to be black nodes. So all that means is that red nodes can be leaves. That's all this last one says. This last thing here. And the last point, the number of black nodes on any path remains the same. So if you take any path that starts at a root and goes to a leaf, you have to have the same number of black nodes on any of those paths. And if you just obey these properties, then you're guaranteed that you'll have a valid red-black tree, and in fact, a balanced binary search tree, as long as it's also a binary search tree. And yeah, so these are the 4 properties that you know about red-black trees, and the kind of things that we'd ever ask you might look something like this. So yeah, you have to figure out whether these are true or false. So yeah. What are your thoughts?
The first one is true.
Mhm.
The second one is false because the color is reassigned. And the third one, number of nodes. No, false.
Yeah, nice job. Yes, that's all right. So as you mentioned, that's exactly what they are. That's exactly why they exist. It's the self-balancing binary trees. And this is also absolutely false, right? So like, well, I put a check because it was right, but like it is false. We'll put an X, I guess. So nodes in a red black tree have one color. You cannot be reassigned, right? Absolutely false because, as you mentioned, they are reassigned. And this is also absolutely false because it's not the number of red nodes on any path which is the same. It's the number of black nodes on any path which is the same. Okay, so stop question, is it true, false, false? Yeah, and for the reasons we mentioned. Okay, so then on B trees. So B trees, which we talked about a couple weeks ago, they're self-balancing trees. They can store huge amounts of data for fast query and retrieval. And they're kind of, yeah, like trees inside of trees. So, okay. And they have multiple key value pairs in each node, sorted ascendingly by keys. Binary tree, each node has up to n children. And the properties of them are all nodes have at most n children. The root is a leaf or has somewhere between 2 and n children. Internal leaves, which are not leaf nodes, or have ceiling n over 2 to n children, and non-leaf or internal nodes have maximum and maximum keys. And L is the number of keys a node can have as a leaf. Maximum number of keys a leaf can have. So these are the main properties of each tree, because the kind of questions we might ask you mostly center around like what we'll get to in the next slide. But the first thing is that, yeah, like it is important kind of to understand that they're self-balancing trees, not binary, just self-balancing trees. They might have more than 2 children per node. And yeah, they have multiple key value pairs in each node, and it's an n-ary tree, right? So, but the main kind of things we might ask you are something like this. Oh, well, next slide. Sorry. But B plus, first of all, B plus trees. B plus trees are very similar to B trees, except for the fact that each non-leaf node contains only keys. So it's not a leaf node, it contains nothing but keys. Or sorry, if it's yeah, if it's a leaf node, it only contains the keys, or like contains the values, right? But if it's not a leaf node, like if it's an internal node in the tree, then it doesn't contain the values we care about. It only contains keys which help you figure out which leaf to go to. All data is only stored in leaves. And the level at the bottom is linked, like has leaves linked together. So you have like a linked list of values. So that's the distinction between B plus trees. Otherwise, it's the same. But Yeah, we do. Okay. So why another balance tree? Why do we use B and B plus trees? Well, they're really helpful because they act kind of like cache blocks where each block contains a lot of data. You can pull from external blocks of memory, and it can pull in like a big block of data at once, which is really, really helpful if you think about it, because if data is really, you're able to bring in a large block of data from like external memory, and if you had to take each one by one from external memory, that would be very, very slow. But if you take all of it at once from external memory and bring it in as one big block, that'll be a lot faster because, well, now all the data is near where your like processor is, right? And it's gonna be able to be a lot faster in getting that data. And also because like data that's near data you're currently using is gonna be more likely to be used. Like for example, with an array, if I'm using an array and data that's like, if I'm in position 0, probably next is like position 1 that I'm gonna access, right? Like before. I mean, that's not so important that you need to know, but that gives you maybe an understanding of why we care about pulling external blocks of data rather than data one by one. That's why we use them. That could be in the plus tree. So yeah, and you can index file systems and databases with them. But now the main kind of questions we would ask are things like this. If you're given a completely full B tree with n equals 3, l equals 3, and height equals 2, I mean, I think it's kind of weird to call it height equals 2 because it has 3 levels, but whatever. Notice there are 3 levels. N equals 3 and l equals 3. How many unique keys are in the B tree, full B tree? And yeah, if you don't know, it's okay. It's kind of.
I'm solving it.
Oh, okay, cool. That's right. It's one of those things you just have to draw out to know.
Yeah, but I switched N and L, so I had to do it again.
Oh,
Well, then I got confused, but my first answer is 35, so I'll go with that, and then you
okay.
can show it.
Yeah, that's a good answer. So let's see. Let's try and work this one out. So remember, it's a B tree and not a B plus tree. So with a B tree, we do care about internal nodes. So n equals 3, which means that each node can have at most 3 children. And it also means that each node, because the full tree, right, every node will have 3 children. But also, we know that each internal node will also have 3 minus 1 values. So let's draw that. So that means that we're going to have something like this. A root, right, just not a leaf, so have up to 2 values. And then because n equals 3 and it's full, this is going to have 3 children. And each of those is going to be an internal node also. And so each of them will only have 2 values, and then each of them will have 3 children. But now each of those 3 children, each of these 3 children on each of these 3 children, so all of the grandchildren of the root, because their leaves can have up to L equals 3 values. So this is going to look like this. And okay, I'm not going to keep drawing all of these out. I'll just put 3 to denote the fact there are 3 for all of them. And we'll just ... so on. So how many total do we have? Well, we have 3 here. We have 3 here, 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 3 here. So that's 3 times 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 times 9 so far. But then also we have 1, 2, 3, 4, 5, 6, 7, 8. So 3 times 9 plus another 8. And as a result, we get 35. It's awesome job. Yep, it's 35. 35 unique keys. And so maybe the next drawing will make it even more clear to us what's going on. Because, yeah. Yep, so that's how we calculated it.
Can you go back to the B tree slide?
Yeah, absolutely.
When it says online, wait, so N is the number of keys and then L is for the number of children?
So yes, n is the number, well, not quite the number of keys. N is the number of like, okay, n is the number of children each node can have in like every node can have up to n children. But every internal node can have up to n minus 1 keys. L is just a leaf.
Okay, so L is for leaf. Okay.
Yeah, it's the number of keys a leaf can have. And so yeah, just looking at this example and kind of like with that in mind, let's see the drawing of it. What we notice is that for here, because L is 3, each of the leaf nodes can have 3 keys, and each internal node can have 2 keys, 3 minus 1. And then also each internal node can have 3 children, which is why this one has 3, this one has 3, this one has 3, and this one has 3. And so that's this drawing.
I was thinking that it was that the keys have one less, that the internal have one less key than the leaves, but those numbers are independent.
Yeah, they're independent.
Gotcha.
And then, so going off of that, that's for a full B tree. What about a full B plus tree instead? How does it change?
So this one would just be 27 because it's basically the same as the last one, but it's only the leaves.
That's exactly right. Yep. Because with the B plus tree, we asked how many unique keys there are. Internal nodes don't have unique keys. And so as a result, it's just the 35 minus the 8 internal nodes, 27. So I guess there's no drawing here, but if we go back to this one, like we would say, okay, it's exactly this, but we just don't care about internal nodes because they don't have unique values, only leaves. Awesome, yeah. So now splay trees. So with splay trees,
Before you do splay trees, when would you use like a B versus B plus tree? Like one over the other?
Yeah, so it's a good question. To be honest, I'm not entirely sure, but I think you might want to use a B plus tree if you're going to access all the data like consecutively. So it's good in the sense that if you want to be able to get like one value right after another, you want to get them all sequentially, you have the linked list layer of leaves. So that might be a good use of B plus trees because you can get them all sequentially. Just like once you have one, you just go in order to get the rest.
Okay.
I've talked about it though. But as for actual implementations, I'm not really sure.
All right, thank you.
But for splay trees, they ask a really quick. For splay trees, they're also self-balancing binary search trees. just like red-black trees or ABL trees, but they're a little bit different in that after you access the node, it moves to the root via zigzag rotations. So here, the most recently accessed node we know was 1, right? We see 1, and we do zigzag rotations to get 1 to be the root. And yeah, and it's best for ensuring that most commonly accessed nodes have the least access time. So you might use this for something like caching, because most recently accessed nodes are the easiest to access or the fastest to access. So as a whole question, what was the last node that was accessed in the Splay tree? Given that this is what the Splay tree looks like now.
5.
Yep, exactly. 5, yeah. And it's 5 because 5 is 0 now. So we must have done zigzag rotations to get it to the root. Okay, now here's some priority queues. So heaps and priority queues up, as we mentioned in the past.
With the Splay tree, like if I said like the second most recent one, it could be either 1 or 9 equally.
It can be 1 or 9, yeah. And I think not even necessarily. Wait, let's see. Because like before, the tree might have looked something like this. Actually, it might have been like 6. Like I think this is also possible. It was 6, 9, 5, 1, 3, 4. So in that case, the second most recently accessed node was 6. So we don't really know.
Oh, okay. Thank you.
Yeah, no problem. Although in general, like things that were more recently accessed will be closer to the top in general.
So it's more likely to be, but not
It is more likely, yeah, to be like 1 or 9. Yeah,
that's all.
that's good question. Okay, cool. So then for heaps and priority queues, a priority queue is a special type of queue in which every element is assigned some sort of priority. An element with high priority is dequeued before an element with low priority. Right, so it's just like, as I mentioned before, just like a regular queue, except priority is defined differently than most recently inserted, or like the first inserted node or value is not necessarily the first node. It can have different priority than that. So like the largest value gets the smallest value. And if they have the same priority, then we just resort to the regular queue property and yeah, to give them in the order in which they're put into the queue. And for priority queues, you insert peak highest priority, pop highest priority. And that's it. And yeah, you might have the same operations for the lowest priority, depending on implementations in general. For priority queues, like with max heap versus min heap. Like max heap, you'll have the largest element as the first one out, or if you use a max heap versus min heap to implement the priority queue, whereas min heap, the smallest one, will be the first one out. So binary heap is generally how we actually make a priority queue. It's a complete binary tree, and it really just satisfies one property, which is a heap ordering property, which is just that elements which every element with higher priority, or every element has higher priority than its children. And like that's it. That's what makes a heap. And if it's a binary heap, it's also a binary tree. And yeah, max heaps and min heaps, like talk about those where max heap, larger values are at top, min heap, smaller values are at top. Yeah, and you can only remove the root from a heap. So extract min or extract max. But they take only takes log n time to remove. To actually remove it takes O1 time, but then you have to call heapify, and that takes log n. You insert it at the end and then heapify it up. So this is what min heaps and max heap looks like. Notice that with min heaps, the smallest value is at the root and every subtree. And for every subtree, the smallest value is the root. So smaller values are above larger values. With a max heap, the larger values are above the smaller values. And every subtree has a root, which is the largest value in that subtree. Which is just another way of saying the exact same thing. Like basically, like smallest value being the smallest value of every subtree being the root of that subtree is just the same thing as saying like every node is smaller than its children. And again, we have the array representation for heap, and we talked about this last week a bit. where if you want to find the left child for a 0 indexed array, it's 2i plus 1, and for a right indexed array, it's 2i plus 2. And the parent is I minus 1 over 2. But then we just do integer division, right? So we round down. That's it. That's just how we find the children and the parents for a heap. Our full question now, what's the array representation of this heap?
A.
Awesome. Yeah, it is A. So as Rich mentioned, it's A because if we try to represent this with an array, the first thing we're going to have is the root. So, I mean, that rules out D right away. But then we have the left child of the root and the right child of the root is the next two elements in that order. So 88, 66, 77. On A is the only one that follows that. So it's going to be A. And we can keep going from there. So if we want to keep going from there, 88, 66, 77. And then we take the left child is 66, then the right child is 66, and the left child is 77, the right child is 77. And the left child is 33, right child is 33, and the left child is 44. And that's all. And that's what we get. Okay. And in the insert operation on a heap, where do we initially insert the new node?
C.
Yep, exactly right. Yeah, we have to insert at the very end of the array, or at like the end of the heap. So the next bottom right leaf. And then we heapify up. And so for heap insertion, if we start with a min heap, when we insert a node, if we have our heap, we have our heap size, we have our insert value. Initially, what we do is we do heap size minus 1 equals insert value. So you put it in the last place, you increase the heap size, and you call percolate up or heapify up. Both are perfectly fine ways of calling the same thing. Like percolate up and heapify up just mean the same thing. Where you just, go up the tree and keep trying to swap until you finally reach something. With the min heap, keep trying to swap until you find something that's small, a parent that's smaller, or until you reach the root, and then there's nothing to swap with anymore. So as an example, we insert 1, and we need to call heapify up. So you check 1 against its parent. And when you check 1 against its parent, well, okay, that's going to mean heapify up. And you find the parent's index with child minus 1 over 2. Because that's what we do for finding indices, right? With 0 indexed array. And then if the heap's child is less than the heap parent, so if the value in the parent is less or is greater than the value in the child for a min heap, then we actually need to do a swap. And when we do a swap, we're swapping the child and the parent. So 1 and 12 are going to swap. Then we're going to heapify up. But now the child index is the index where 12 was before, because that's not where 1 is, right? So now we need to check if 1 is smaller than its new parent, which in this case is going to be where 5 is. So that's exactly what we're going to do. We're going to see that happen. We're going to see that play out. Once it's less than 12, we swap. Then we do the same thing again, where we check 1 against 5. And it's less, so we swap. But now we try and check 1 against its parent, and we can't, right? Because it doesn't have a parent. Okay. So for max heap insertion, we have pseudocode here. And yeah, as we mentioned before, like we looked at the pseudocode, it's the same thing. We have your parent index and your child index, which was the previous parent. The new parent index, or the new child index becomes what the parent index was before, because that's the new location here, right? And then you just, if you do a swap, after you do a swap. So yeah, we kind of just walk through this code. But here it is in full for you guys to see. But okay, let's see this full question. In delete operation on a heap, which node do we always delete?
The root.
Exactly right. Yep. We delete the root. And the root is the only one you have access to. And heap, that's the one you can delete. So for heap deletion, let's look at a max heap. And so what we do first is you delete the root by first assigning the root the value of the last element in the heap. You put it inside of where the root is, and then you decrease the size of the heap by 1 because the heap size is smaller now, right? Because you deleted something. And then you call percolate down or heapify down, if we prefer to call it that. That's fine. So in this case, right, we delete 66 and put a 12 there. Put a 12 there, and we decrease the size of the heap. We call heapify down. And so for heapify down, essentially what we do is we just check like the parent, or so the new root, check it against both of its children. And for max heap, we need to find the maximum value. So the maximum is either the parent, it's the right child, or the left child. In this case, we know it's the left child. And so the left child will become the new root. So what we need to do is we need to swap the left child and the root. So we have these cases, right? If right is less than heap size, or if like, oh, and heap right is greater than heap max index, and if heap left is greater than heap max index. So the first part of the if statement, just make sure it keeps in balance. So these are there to make sure that we're in balance still. And if we are, then we make the check of is left greater than, is right greater than. And if it is, like the only case we're actually going to look at here that matters, well, we actually go into right first, because in this case, 37 is larger than 12. So for 37 larger than 12, we do max and equals, right? But here, then we also do left, right? Because left is less than heap size. Because 45 is a valid place in the array. And also it's greater than the new max, which was 37. So 45 is larger. So max index becomes left. So left is 2 times parent plus 1. So that's just 1. Or if 4 is 0 indexing, it's 1. So now our max index is 1. If max index is not equal to the parent, you swap. And then you call heapify down again. So just recursively. So 45 and 12 are going to swap. So if 45 is the new root, then we're going to recursively call heapify down. With 12 here. And now we're going to try and do the same thing again, but we're going to notice that 12 is in fact greater than both 10 and 5. So we aren't going to swap down anymore. And then we're done. So let's look through this, see the animation for it. Yep, so this is the code as we go. And again, we try and swap with either of them. We can't, there's no need to, and we're done. And for delete node, it works the same with min or max heap. Really, the only difference is going to be the less than or greater than signs here. So it's going to be less, here it's going to be greater than, and this is going to be greater. Like for a min heap, I think, yeah, this is the only change. We just change these greater than signs to less than signs. And then that's basically it. It's really not much of a change. And then, yeah, this is for, yeah, and there we go. For heapify down, the only difference is we swapped the signs. So heap performance, what's time complexity of adding or deleting an element to or from a heap?
I want to say log n, but I'm not sure.
Okay, yeah. And yeah, you're absolutely right. It is log n. And
Okay.
yeah. And the reason why it's log n, right, is because the height of the tree is always going to be log n. And let's just look at this, right, for a second. Like if we have a heap, the first thing, let's look at deletion first. So for deletion, the first thing we do is we get rid of the root. That takes O1 time. Then we swap the last one into the position where the old root was. That also takes O1 time. And then for each time we like heapify down, we do a comparison against a child. And the comparison only takes O1 time. And the number of comparisons we're going to have to make grows only with respect to the height of the tree, right? Because we make one swap for every level. Well, the height of the tree is log n,
Hmm.
right? And the height of the tree is log n because heaps are complete binary trees. And because they're complete, they're balanced. Okay? So the height is only log n. So the height is only log n. Then deletion, we'll only have to make log n checks in our heapify method. So it takes log n time. As for insertion, if we look at insertion here, I don't need to go all the way back. Let's just go here, I guess. So here, if we inserted 5 initially, like at the end, or I guess we inserted 1 originally at the end, then when we did that, well, it took just O1 time to insert it at the end of the array or the end of the heap. And then for every level we want to swap it into, we check if it's smaller than, this was a min heap, so we check if it's smaller than its parent. But again, the height of the tree is log n, so we only make log n swaps, and each swap takes O1 time. So the total time is full log n. Okay.
That makes sense. For an answer choice like C, couldn't you like you can automatically eliminate that because that would just be the same as ON, right?
Yep. Yeah, exactly. Actually, that's a good point. Yeah. Like I guess if you see something like this along with D, like you can just say, okay, these are probably wrong because they're the same. Right? Yeah, you're right. Good catch.
Okay.
Okay. So yeah, for an array with n elements, what would be the time complexity of building a heap based on inserting all the n elements of the array into a new heap?
B and log n.
Yep. That would be exactly right. And log. Because the total time will be n times, because you have n elements, the time complexity of adding a single element to the heap. So you have to remove every element and then insert it into a new heap. And so removal takes log n, and then insertion takes log n. So yeah, it would take n log n time.
This no, I think you were about to say it.
Oh, okay, yeah. And so like with the if you do it with the regular heap, if in place, it only takes O(n) time, but here we're having to move it over to a different heap, and so it takes n log n.
Wait, say the second.
Okay.
Say that again.
Yeah. So if you're
I
building,
remember that we talked about like if you show the math and on average it comes out to O of n time, but it could be the worst case of O and log n.
well, actually the worst. Okay, so yeah, let me try and talk about it. So actually the worst case for that, for building a heap in place, the worst case for that is still O(n) if you build it properly. The problem is here we're not building it in place. We have to take all the elements from a heap and we have to insert them into a new heap. So that means we originally have a heap and we have to take all the elements from the heap and move them into a new heap. Well, what that requires us to do is do n removals and then n insertions in the new heap. So even though taking an array and making it a heap on its own takes only O(n) time, we'd have to remove every element from our heap, and that alone takes n log n time. Because n removals is always going to take n log n. So that's but if we didn't have to use a new array or a new heap, if we just had our current array, unsorted, sorted, doesn't matter, whatever, and we just wanted to make a heap from that, that would take only O(n) time.
So like building a heap in place is just like moving the elements within the array that they're already in.
Yeah. Yeah.
Okay.
Right. Yep. So this in particular we're taking on, the other one, yeah. Okay. And I think that's actually, yeah, that's it. So yeah. Thanks. Do you have any other questions?
Possibly. Hold on.
Okay. Yeah, I do appreciate the questions because they also force me to think a little bit. That's good.
No, I don't think I have any other questions.
Okay.
The unit that's like in this week's like reading is not on the midterm, right?
It shouldn't be. No, I
Sorting?
think this. Yeah, this is all that's going to be on the midterm.
All right. Okay, thank you.
Yeah.
Have a good night.
Yeah.